Okay, welcome back. So, just to recapitulate what we have been doing, we derived the one dimensional version of the entropy of a classical gas of molecules and made sure that it is extensive by taking into account the permutation of the number of particles, thereby resolving what we call the Gibbs paradox. So, I also encouraged you later on in this slide to do this or think of this as a homework, namely find the entropy or generalize the one dimensional example to 3 dimensions and get the what is known as the Secours tetrode formula of the entropy of an ideal gas. The way you do that is obviously very similar to what we were doing in 1D, and that is it involves simply evaluating such an integral, and the way you do this is to rewrite the Dirac delta function as a Fourier transform, and then you go ahead and do the rest. So, I am going to leave this to you as an exercise, and when you finish with it you end up with this formula, and this is the famous Secours tetrode formula of the entropy of a classical ideal gas. So, notice that how we derived this in the traditional way, namely the way it was done by the pioneers, and that is to divide up the phase space into pixels and populate those pixels with the molecules, and then learn how to count the various microstates subject to various constraints. So, that is the conventional way of doing it, and that gave us a Secours tetrode formula. Now, of course, there is a more sort of sophisticated way of doing the same thing, and that is remember that we took great pains in deriving the entropy of a quantum ideal gas, and we could go ahead and use that expression and take the classical limit of that expression and also arrive at the same formula. So, it is instructive to do it both ways, so that you know the whole subject is self consistent. All right. So, let us get on with it. So, how do we do that? So, recall that in the case of classical, if you want to take the classical limit of a quantum system, you are compelled to choose the chemical potential in such a way that this quantity, in fact, this is called the reciprocal of fugacity. E raised to beta mu is widely called fugacity, and so this would be reciprocal of fugacity, or 1 divided by fugacity. So, and this is basically chosen to be proportional to h to the power 3 inverse 3. So, that is because when you do this you are able to successfully handle the classical limit of a quantum system. That is we have shown this earlier. So, as a result, if I select this to be my constant C 0, and the energy density in the classical limit comes out to be this expression. So, it is insensitive to whether it is fermions or bosons. The moment you go to the classical limit, you see the expressions do not care anymore whether you are describing bosons or fermions. After all, we are now entering the classical limit. So, when you do that, you end up having to do this integral, and then you get this expression for the energy per unit volume of a classical ideal gas. Now, you could do the same thing with pressure, and you should understand why I am doing this first, because if you recall, the entropy expression really had all these things in it, the energy density, energy per unit volume, pressure, and so on. So, I had better calculate these first. So, the pressure, and of course, these will be useful independently later on. So, the pressure of a classical ideal gas is the h tends to 0, Planck's constant tends to 0 limit of the quantum version of the same quantity. And when you do this, when you take this limit, you end up with this expression, this simple looking expression, which of course now does not involve either q, which determines whether it is bosons or fermions, nor does it involve h, which is Planck's constant. All right. So, lastly, we'll also be needing something called beta mu in our expression for the entropy has this quantity, and this this Planck's constant finally refuses to go away. You will see that the expression for the entropy still involves Planck's constant, and that should not come as a surprise, because if you recall in the earlier expression there was this h prime, which really didn't have any intrinsic meaning other than what was this h prime. If you recall, it was the size of the pixel. So, that means I divided up the phase space, which is made of x coordinates and p coordinates, into small bits and pieces of small squares, and the area of each square, small square, was h prime. Now, of course, that h prime being a square in phase space, in one dimensional phase space, has the dimensions of momentum times length, and that is of course also the dimensions of Planck's constant. So, you should not be surprised if there is some relation between the smallest pixel size that I have selected. Notice this is an artificial coarse graining, and that is survives in this expression. So, it does not go away. So, we are stuck with it. So, now we are also similarly going to be stuck with Planck's constant, even though we are studying the classical limit of an ideal gas. So, we end up with this expression for beta mu well in the classical limit, and this is what it is. It is just obtained by taking logarithm on both sides of this expression. This was a choice we made in order to recover the classical limit. Alright, so now let me go ahead and substitute all these expressions into the entropy functions. So, notice that the entropy function has energy per unit volume, which we have just derived. It has pressure, which we have just derived, and beta mu, which we have selected earlier. So, we have derived the classical limits of the energy density of the pressure and of beta mu, which we selected in order to make all this work. And we substitute now all those expressions into this formula for the entropy of a quantum ideal gas in the classical limit, and then we end up with this expression. So, so now what we are going to do, so this is the answer for the entropy of a classical ideal gas viewed as the classical limit of a quantum entropy. So, now notice that we have also derived the familiar Secours tetrode formula directly by phase space counting, and we got this expression. Obviously, we want these two expressions to be the same, and then when we equate these two, we see that that means basically we equate the logarithms here, and that effectively tells you that the size of the pixel or the area of that pixel that I was talking about is really related to Planck's constant h, the original Planck's constant, not divided by 2 pi. So, it is just proportional to some number times Planck's constant. So, try as you might, you will never be able to get rid of the effects of quantum mechanics completely, and so that is telling you that basically at the subatomic level there is some amount of quantum mechanics is going to survive no matter how hard you try. So, the expressions that we derived for P and energy per unit volume uv is not merely to as a intermediate step for obtaining the entropy, but it is interesting in its own right, because after all, if you know that rho is nothing but the number of particles per unit volume, and then you can extract the total energy by multiplying both sides by volume, and recall that beta was just inverse temperature. So, when you do that, you get an expression which is very familiar to you, which is total energy is 3/2 times number of particles times temperature, with of course, the Boltzmann constant being set to 1, because I am measuring temperature in energy units, as I have told you repeatedly earlier. Okay, so, so that is precisely what I am getting here. So, when I do that, when I multiply both sides by V, I end up getting this familiar expression. So, I had just derived this expression here which is P is equal to rho by beta, and then I rewrite it in terms of something more familiar, namely temperature and volume and so on, and you get this equation of state of a classical ideal gas. P v equals n k T, but k is 1. So, P v is n T. So, you see we have been successful in doing three things. One is derive the equation of state of a classical ideal gas, find the relationship between the total internal energy of a classical ideal gas in terms of temperature, and finally derive an expression for the entropy function of a classical ideal gas. So, all these are extremely important calculations made possible only because we have understood statistical mechanics sufficiently well. We have understood what entropy is and how it is related to counting the number of microstates subject to various constraints. Well, we still haven't fully understood what pressure and temperature mean, other than the fact that it's the derivative of the entropy function relative to various other independent parameters, but that's a very mathematical and opaque way of thinking about it. So, obviously, there is a more physical meaning for pressure and temperature, which we haven't discussed yet, and that's something I am going to do subsequently. But that apart, we have successfully written down the equation of state, total internal energy, and the entropy function of a classical ideal gas. So, now let me get on to this question that I just mentioned, namely what is temperature, what are these quantities, other than the fact that they are simply we know that they are derivatives formally in thermodynamics. Absolute temperature is defined as the rate of change of entropy with internal energy, and it is the reciprocal of that, the slope of the entropy function versus the internal energy, reciprocal of that slope. So, pressure is similarly defined as the ratio of these two slopes, that means the slope of the entropy versus volume and the slope of entropy versus internal energy. And similarly, chemical potential is similarly defined in this way. So, as the ratio of slopes of the appropriate slopes of the entropy function. So, of course, this is a mathematical definition, it does not teach you anything about what it means physically. After all, we know that temperature has a very concrete physical meaning which we experience on a daily basis. So does pressure, maybe not chemical potential, but unless you are chemist or somebody who does laboratory experiments in chemistry, well, we do not experience that on a daily basis, but pressure and temperature we always experience on a daily basis, all of us. So, we had better be able to relate these formal mathematical definitions to something more tangible. Okay, let me try and do that. So, in order to do this, what we should be doing is imagining a system which, say, for argument's sake, let us assume that it contains energy U1 and it has volume V1 and the number of molecules in that system is N1. I am going to distinguish this system from what I call a surroundings or reservoir. So, imagine that there is a system which is surrounded by some huge reservoir, and that reservoir could be, for example, the atmosphere itself. So, you can have a system which could be a gas which is trapped in a container, and it is placed in the Earth's atmosphere, and the atmosphere itself is the reservoir, and the gas that is trapped in your container is your system. So, now what we are going to do is that we are going to allow the energy to be exchanged. So, we assume that the containers have rigid walls, for example, the containers of the gas that we have called the system has rigid walls. So, let us imagine they have rigid walls, and we are going to also assume that it is not isolated. In other words, the system is not isolated, it can exchange energy with surroundings. So, how do you accomplish that with rigid walls? It is very easy. So, all you do is you assume that your walls of your container that contain the gas are not thermally insulating. So, they are kind of thermally conducting walls. So, as a result, heat can flow in and escape from the system. So, as a result, energy gets exchanged from the system and the reservoir. So, you allow that. So, as a result, what is really fixed is not the total internal energy of the system, which I have called U1, but rather it is the sum of the total internal energy of the system plus the reservoir. So, in other words, that is going to be U1 plus U2, which is fixed. So, I am going to call that capital U. I am going to call U1 plus U2 as capital U, and so as a result U2 is going to be capital U minus U1. So, imagine that omega 1 is the number of ways in which you can rearrange the microstates of the system such that its total internal energy is U1, and of course, because the other ones are fixed. So, notice that my walls are rigid, the walls of my system are rigid. So, as a result, the volume of the system is always fixed at V1, and I do not allow particles to escape in or out of the system. So, the number of particles is fixed as N1. So, same with the reservoir. So, the volume of the reservoir is fixed as V2, which is enormous compared to V1, and N2 is the number of particles, which is also fixed, but it is also enormous compared to the number of particles in the system. So, now the only thing that is the other thing which is remaining is the internal energy, which is not fixed. So, in other words, U1 is not fixed and U2 is not fixed, but their sum is fixed. So, in other words, put together it is fixed, but individually they are not fixed. So, as a result, I can suppress the volume label V1 and the number of particles label N1 because they are fixed. So, I am going to suppress that, and I am going to refer to omega U1 as the number of ways in which I can rearrange my microstates of my system, which is a gas. So, the number of ways I can rearrange my microstates such that the total internal energy is U1, and of course, the other parameters are what I just told you. So, similarly, I label omega 2 U2 to be the total number of ways in which I can rearrange the microstates of my huge reservoir such that its total internal energy is U2. So, notice that because U1 and U2 are not fixed and their sum is fixed, that the net number of ways in which I can rearrange the microstates of the combined system such that the total internal energy of both put together is U is this sum. So, it is this the first product will tell me that if the system has U1 energy, the reservoir has U minus U1 energy, then of course, the overall number of ways of rearranging the microstates of both the systems and the reservoir put together is this product of omega 1 times omega 2. But then I have to ask myself, I have to repeat this calculation for various different U1s, and then because for each U1 there is going to be a certain way of doing it, and for a different U1 there is a certain other number of ways of rearranging the microstates, and these are independent rearrangements. So, because they are independent, I will have to add them all up in this fashion and get a net number of ways in which I can rearrange the number of microstates of both the system and the reservoir. And rewritten in terms of entropy, it is going to look like this. Now, what I am going to do is, I am going to ask myself, what is the most probable value of this U1? So, notice that U1 is not fixed. So, it can fluctuate wildly because U1 is being exchanged with the surroundings, but then I can still legitimately ask the question, what is the most probable value of U1? So, clearly the most probable value of U1 is that U1 which makes this quantity a maximum. So, in other words, we have anticipate that if I plot this product as a function of U1, it is going to peak at some U1 star. So, it is going to peak at this U1 star, and that is something that I refer to as the most probable value of the internal energy of my system. So, how do you determine that? And the way you determine that is to simply differentiate this quantity and set it equal to 0 at u star, as you very well know. That is how you find the extremum of a function. And given that these omegas can be expressed in terms of the entropy, that eventually amounts to doing this. So, it amounts to equating the so notice that if I do it this way, I can do it with the entropy, because after all it is extremizing omega products of omegas is same as extremizing the log of the product of omegas, and then the derivative of the log is the logs are just the entropies, the sum of the entropies, and the derivatives would then correspond to this sort of an expression. Equals 0. And when you do that, you get this expression, which is ds1 by du1. So, this is plus, this is plus, because after all if you take the log, you get the sum of the entropies, it is the omega, that is the product. So, if I take the derivative with respect to u1, I get this plus, and then notice that differentiating with respect to u1 is same as differentiating with respect to u2, which is u minus u1, and flipping the sign. So, then so in other words, this is going to be minus ds2 by du2 equals 0. So, the extremum is achieved when you equate the slope of the entropy with respect to the internal energy of the system and the surroundings. So, recall that this slope is nothing but the thermodynamic temperature, and that is how we have defined thermodynamic temperature. So, now you have a physical meaning for thermodynamic temperature. So, now you can also choose to alternatively define thermodynamic temperature as that quantity which equalizes when a system is allowed to be in contact with a reservoir and allowed to exchange energy. So, in other words, the quantity that is common to the system and the reservoir in thermal equilibrium is precisely temperature or something related to it. So, in particular it depends on how you define it. So, we have chosen to define this as reciprocal of temperature. So, the temperature concept is basically a concept which just tells you that it is that attribute of a system which becomes the same as the corresponding attribute of the reservoir when the two are in thermal contact with each other, and sufficient time is allowed to elapse, so that they come to an equilibrium. All right. So, that is what temperature means intuitively also, and so it is nice that we have successfully related a mathematical definition, namely the inverse of temperature being the slope of the entropy versus internal energy, rather abstract and sort of opaque definition, and we have linked it to thermal equilibrium and how when a system and reservoir come into contact, the attribute that is common to the two is exactly what is known as temperature. So, you can go ahead and do the same thing with pressure. So, with pressure, of course, what you have to do is that you have to make sure that the walls of your container are not rigid. So, in other words, the gas that is in the container is free to expand and contract. So, you repeat this exercise where the total volume of the combined system of the system and the reservoir is fixed. So, in other words, V1 plus V2 is constant, which I call capital V. So, but V1 and V2 can change by themselves. So, of course, if you allow for gases to expand and contract, and naturally the work gets done, and as a result the internal energy also gets exchanged whether you like it or not. So, the mere fact that you allow for gases to expand, the walls of the container to be not rigid, implies that work gets done or is done on the system. So, as a result that work gets transmitted to the internal energy of the system sometimes, and as a result you can't really have it is not easy to have a mechanism by which only volume changes, but internal energy does not change. So, typically we end up allowing for both to get exchanged, and so that is why I have allowed for the internal energy to be exchanged and volume to be also exchanged. But however, it is very easy to prevent molecules themselves from being exchanged, because all you have to do is have an impenetrable wall where molecules cannot diffuse into the reservoir, or molecules from the reservoir cannot diffuse into the system. So, that is easily accomplished. So, as a result, I can ask similar questions about when is the most probable volume and when is the most probable internal energy achieved, and that is when the this combined entropy gets extremized. So, in this case maximized. So, what I have to do is I have to find the so I am not going to repeat this calculation, it is very similar to what we did earlier. So, if I do it for the volume, I end up asserting that the slope of the internal energy with volume has to be equated in equilibrium to the slope of the internal energy of the volume of the reservoir. So, the system's slope is equal to the reservoir slope, and notice that the slope of the entropy with the volume is nothing but the ratio of pressure and temperature, and it involves. So, as a result, at equilibrium you end up equating the ratio of the pressure and temperature of the system with the ratio of pressure and temperature of the reservoir. But notice that I have also allowed for energy to be exchanged. So, as a result, the temperatures were anyway equal to begin with. So, because the temperatures were equal to begin with, that implies the pressures are also equal. So, if in a situation where I allow both the volume and the internal energy to exchange, then you see that there are two aspects or attributes of the system that become equal to the corresponding attributes of the reservoir, and those two attributes are pressure and temperature. Well, okay, there is a further concept that is useful. I really want to go back and ask myself, what is this net way of rearranging the microstates of the combined system look like? How does that look like? So, all you have to do is go ahead and replace the entropy. So, notice that we have taken pains to point out the energy that maximizes this product, that is e raised to s1 times e raised to s2 is maximized at or close to u equals u1 star. So, the most probable value of the energy is the place at which this product gets maximized. So, it stands to reason that to a crude first approximation, we may easily replace this summation. We may ignore that we have to sum over all the energies, rather we just make do with the energy which corresponds to the most probable value, or the one that maximizes this. Of course, at this stage it is not very convincing, because I have to convince you that by doing this I will not be making a huge mistake by ignoring other energies that may be close to this most probable energy. So, I will do that subsequently. So, we will have to actually what is called compute what are called fluctuations around the most probable state, and then we have to convince ourselves that under suitable circumstances those fluctuations are suppressed, and as a result we are justified in ignoring them in the first place. So, you will have to take my word for it right now. So, I am going to ignore those fluctuations and assert that the most probable value for the energy is the only energy that matters, and I am going to simply replace u1 by u1 star. So, because u1s are anyway very small compared to the total energy u, I can do a Taylor series of S2 around u1 equal to 0, and then I get this Taylor series. So, notice that this is same as asserting that this S of S2 of u2, which is the reservoir's entropy, is same as the reservoir's entropy when the system has no internal energy at all, minus the internal energy of the reservoir divided by the common absolute temperature. This is just Taylor expansion, Taylor series to first order in u1. So, now I am going to go ahead and substitute this expression here. I have already done that here. This is S2, and then I end up getting this product which is S1 times S2 U2, which I have written like this. Now, of course, I can pull this S2 U outside, and if I just focus on the most probable energy contributions, so I end up with this difference, that is the entropy of the system at its most probable energy minus the most probable energy divided by absolute temperature. So, this is related to what is known as Helmholtz free energy. So, we denote this by minus F by T, which is beta is, remember, is 1 by T. So, we call this difference as minus beta F, and F is sometimes it is also denoted by A. A is some German word for work that starts with A. So, but anyway, F and A are common letters that denote what we call Helmholtz free energy. So, Helmholtz free energy can be thought of as this difference of the most probable internal energy of the system minus the absolute temperature times the entropy of the system at its most probable internal energy. So, I am going to stop here, and in the next hour I am going to just continue with this and see if I can explain to you how to define other types similar to Helmholtz free energy, other type of free energy which is related to allowing the gas to also expand and contract. So, here I have just allowed the internal energy to be exchanged, I did not allow volume to be exchanged or change at all. So, you can do that, and you get a different type of free energy, and that is topic for the next session, and then we will continue from there. Okay, thank you. Hope to join you next time.